I'm live. All right, so 1.0857 grams of a pure sample of a compound containing only carbon, hydrogen, and oxygen was burned in excess oxygen gas. 3.190 grams of carbon dioxide and 0.9360 grams of water were produced. Find the empirical formula of the compound. Okay, so now we're going to subtract the mass of the oxygen from these two things and how much oxygen gas burned. So this was the oxygen gas produced these things. So we got to figure out how much oxygen we burned, because the oxygen came about producing the carbon dioxide and H2O. That's a step that we missed last time. What is about 3? About 4 minus about 1. Well, how much oxygen did react? I guess that calculator's right. You never use your phone as a calculator, always use an actual calculator. So 3 point what?
3.04.
3.04. 03. Okay. Grams of oxygen. All right, so let's convert all these things into moles. So we don't know what the molar mass of this is yet. It's kind of our goal. We do know what the molar mass of oxygen, carbon dioxide, and water is. Oxygen is going to be 32, carbon dioxide is going to be 44, and water is going to be 18. So we can figure out how many moles of everything we have. Then we're going to turn that into moles of each atom. So once we know the moles of the molecules, then we'll find out the moles of the atom. Oh my gosh. They were really not kind on this one. The good news is the AP is not going to be quite this complex. All right, so you do have moles though, right? So moles of oxygen that reacted with it?
I got 0.095.
95. Zero. Okay. And moles of carbon dioxide?
0.0725.
0.725. And the moles of water?
I haven't got it yet.
Okay.
That is actually a much faster way. Oh, that is a lot faster. Ooh. I like the author's way much better than that. It's pretty clever.
Do we have the moles of water?
I got 0.0514.
514. Is that right? Well, can we get a consensus? There are 4 of you. You
I got
got
0.052, but
Did you get
that's not all too different.
I got, yeah, 052. Okay.
052? 0520 like that? Okay. So that's for water, which means that there is 0.0. Multiply that by 2, 1040 moles of hydrogen. Did I do that right? That times that? Because there's H2.
Oh,
Yeah.
Okay.
yeah.
And then 0.0520 moles of oxygen. Got that. Okay, and for carbon dioxide, there's only one carbon, so 0.0725 moles of carbon. And then 0.1450, is that right? Moles of oxygen. We doubled it. It was 0.0725?
Yeah.
Okay. So the author points out that you can actually find the oxygen a little bit easier. You don't even have to do this at all. You don't have to use the oxygen part at all, which is actually pretty cool. So I think this is a faster way to do it. So we're going to pretend that the O2 is not even there. We're just going to ignore it. And there's a faster way. And that faster way is to realize that if you convert the carbon back to grams, the hydrogen back to grams, whatever mass is left over was oxygen. Does that make sense? So you can say, all right, so carbon, if you convert this back to grams of carbon, and hydrogen, if you convert it back to grams of hydrogen, which is actually pretty easy, because it's just 1040, multiply it by 12, that will give you the mass of the C and the H, and whatever's left over is the oxygen, and you can find the moles of the oxygen from the mass. You don't have to do any kind of weird subtracting from the excess oxygen. Okay, so if I realize that I have moles of carbon, moles of oxygen, moles of hydrogen, moles of oxygen, and I say, all right, that 0.1040 moles of hydrogen has a mass of 0.104 grams. Are you with me so far? And you say, all right, that 0.0725 moles of carbon, 0.0725 moles of carbon has a mass of 0.87 grams of carbon, and you add them together, plus 0.1040, you find that the C and the H has a mass of 0.974. And that tells you how much oxygen you had in your compound, in grams. So it's kind of weird going from grams to moles to grams, but it's a more foolproof way than subtracting moles when you have an unknown amount of oxygen. So we're gonna pretend that the oxygen is excess. We're not gonna deal with it. We're gonna deal specifically with the moles and the masses of carbon dioxide and oxygen. So you subtract the 1.0587 from the carbon and the hydrogen's mass, which is 0.974, and you get that the oxygen had a mass of 0.112 grams. Just realizing my. Oh, jeez. Give a kid a Sharpie and he'll draw all over your calculator. Or give a kid a highlighter, draw all over your calculator. All right, so this, so we have the moles of carbon, which is great. We have the moles of hydrogen, which is great. And then this will give us the moles of oxygen. Make sense? I apologize for what's about to come up. And we are going to divide by 16. We're talking about actual atoms of oxygen.
Wait, so what are you doing now?
So now that we know the mass of the carbon and the hydrogen, we subtract it from the mass of the given compound. That gives you the mass of the oxygen. I'm going to convert that to moles of oxygen.
Okay.
And what that's going to give me, I should do it in green. What that's going to give me is my moles that I can use for my empirical formula. So take the 0.112, divide by 16, that's going to be the moles of the oxygen.
Where'd you get 0.974 from?
I added the mass of the carbon and the mass of the hydrogen. We're taking apart the little pieces.
And that's moles of
Probably
oxygen.
check this every time. Oh, good. We're good. I'm sorry. Good. Say again.
That's moles of oxygen in the compound.
Correct. Okay, ignoring all this. They really don't care about that. So this is faster. It's a better way to do this because it's more. It's less virus proof. More virus proof. My answer went away. But what'd you get for the moles of oxygen? You divided 0.112 by 16.
0.007.
0.00. That's not enough significant digits.
70. The calculator.
Yeah.
70. Okay, fair enough. All right, cool. So what we have is C 0.87, H 0.1040. We'll go with 3. So 0 there. O 0.0070. So now we're going to divide all the numbers by the smallest number to get the ratio. So we're going to divide the carbon by the 0.0070, the hydrogen by the 0.0070, and the thing by the 0.070. And that's going to give us our actual ratio, which we can adjust if we need to. And again, I apologize for what I'm about to tell you. What we're going to get is not exactly the same thing. Yeah, it's messed up. What the? Are we sure it's point?
Smallest on bottom.
Are we sure it's 0.0070 or 0.070?
0. It's 2.
Really?
It's 2 zeros.
It certainly is. Yeah. Wow. And 0.07 carbon. Oh, 104. 0.87 carbon. Huh. Carbon numbers are off. Where are carbon numbers off? 3190.
So 0.87 is the grams.
That's fine. Thank you. That number is way too big. 0.0725. That's better. Yeah. Thank you. Thank you. This number is way too big.
So you have to change the hydrogen.
The hydrogen has a molar mass of 1.
Oh, yes.
So the moles and grams are the same. So carbon ratio, or so smallest and the biggest, carbon's ratio down here should be what?
10.4 moles.
10.4. Yeah, and then hydrogen?
14.9.
And oxygen is just 1. Okay. Again, the AD is never going to be something this complex. Here's the problem. We have something at a half. So since we have something at a half, if you ever get, exactly, you double it. If you ever get a 0.3 or a 0.5, you have to triple it or double it. Okay. If you get a 0.1 or a 0.8 or a 0.9, 0.1, 0.2, round down, 0.8, 0.9, round up. Okay, because there's rounding errors throughout this whole process. So because we're close to a half, this has to become C 21, H 30, O not
2.
2. That's the chemical. Now, again, one of my great projects, and I'll probably never get to before I retire, is rewriting all these exercises so they're closer to what the AP is going to give you. The AP is never going to give you something this complex. They usually give you C1H2O2, C2H1O1. That's it. That's about as 1, 2, 3, and 4 is about as complex as they get. In fact, we had one not long ago, either last year or the previous year. The empirical formula was just CH4. Simplest hydrocarbon there it is. Okay, so they're never going to give you something this complex.
What if it's 0.7?
I would say round up. Yeah. They're never going to have you multiply by 2/3. It'll either multiply by 3 or multiply by 2. Yeah. Sorry. I wish I could rewrite some of these exercises, but I didn't.
Let's look up a whole page.
Yeah. Again, you know, like it's really hard when you're practicing and you go in the game. It's like not as hard. This is one of these issues. Like this is way more intense than you're going to do in an actual AP test. In actual AP, you're going to have very small equations. But again, it's just we're practicing. All right. Any other questions before we move on to the lab tomorrow? We're the pre-lab. Hopefully, you guys can open it. It's brand new. It's brand new, and I just wrote it. Modules. It's going to replace lab number 7A. And it is not on here. Gravametric analysis. Oh, it's down here. Out of order. Whatever. Okay, so I will fix the APC stuff. You're looking for gravimetric analysis of a KI tablet. So open that guy. And believe it or not, this is actually an extension of what you did last year. 3, 4 people. Don't blame me. Blame a bunch of researchers in China experimenting on bats and such. Okay, can you open this? All right. Here it is. Their sign. So last year, you dissolved some potassium iodide in one beaker and a lead nitrate in the other beaker, and you put them together and they made a yellow powder. Then you filtered that yellow powder in a funnel. Remember that? And then you threw it, like you let it sit, and it was great, okay? So that's what you did last year. This year, you're doing the same thing, but you're not gonna be using pure potassium iodide. You are gonna be using pure lead nitrate, but you're gonna be using potassium iodide in these tablets. We gotta figure out how much iodine are in these tablets. So I'll go ahead and tell you, it says potassium iodide dietary supplement, 30 milligrams per tablet for short-term use, 60 tablets. And then when you get a tablet like this, it's never a pure chemical. There's always tons of inactive ingredients. One of the big ones, the big inactive ingredient, is silicon dioxide. Does anyone know what silicon dioxide is used for? Glass. Yeah. Silicon dioxide is used for glass. It's basically sand. So what you're eating, in addition to the potassium iodide, and is sand. Why do they put it in there? Why do they add sand?
To make it stick together.
Exactly, make the thing stick together. This is 30 milligrams of potassium iodide. 30 milligrams, which is give you a hint about how big that is. 0.030 grams. This is 30 milligrams. Okay, you can see the 3 digits, milli. So that's not very much. If you tried to have a tablet that was 30 milligrams, the tablet would be like about the size of a BB. And people are like, I'm not going to take that. Doesn't look like it's going to do anything. So they add inactive ingredients to make the tablets bigger. True story. If you give someone the choice of a big vitamin and a small vitamin, they're going to choose the big vitamin because they think it's more powerful and more useful, even though the active ingredients are identical. Psychology. So the tablets are this big. You see these? The vast majority of it is inactive ingredients. The vast majority of it is sand. And something else called cellulose. Cellulose, does anyone know what cellulose is? Wood. It's plant matter. So the inactive ingredients are crystalline cellulose, stearic acid, which we don't care about, and silicon dioxide. So in addition to the potassium iodide, there's wood and sand in these tablets. Every vitamin has these. Because again, if it was just potassium iodide, it'd be this tiny little tablet, and you'd be like, that's not gonna do anything. You put these on, like, yeah, that looks like it's gonna get something done. But it's just sand and wood, which you can't digest. But we can take advantage of this. We can take advantage of the fact that the cellulose and the silicon dioxide don't dissolve, and the potassium iodide does dissolve. You take advantage of that. So what you're going to do is you're going to get some tablets and you're going to grind them up in a mortar and pestle into a powder. Then you're going to dissolve that powder in water, sort of, because you're going to filter out what can be dissolved and what can't be dissolved. So you're going to get a piece of filter paper. So you're going to grind up your tablets. The tablets are going to go into a beaker of water. You're going to add some water, stir it up, and the potassium iodides are going to dissolve. The cellulose and the silicon dioxide will not dissolve. So when you filter it, what goes through the filter? The potassium iodide. And what stays in the filter paper? The sand and the wood, exactly. So we can separate what we care about from what we don't care about by doing an initial filter. Make sense? Then you are going to add some lead nitrate to a beaker, dissolve it, and pour them together. And you're just like last year, the iodine is going to bind to the lead and make yellow lead iodide, which we will then filter out. And we will go through the process to figure out how much iodine was in our original tablets. This is called gravimetric analysis. Gravametric analysis is a fancy way of saying filtering something out. And it's on the AP about every other year, a gravimetric analysis. And in my opinion, way better than the AP lab. Okay, so let's do the pre-lab activity. The reaction of potassium iodide with lead nitrate produces a yellow precipitate of lead iodide. Write the balanced chemical equation for this reaction. All right. Eric, favorite color?
Purple.
Purple. Okay, so first of all, what is the formula for potassium iodide? Who remembers this?
It's Ki.
Yeah. Potassium is a +1 ion. Iodine is a -1 ion. Ki. And then lead-2 nitrate. Nitrate is NO3. Does anyone remember what the charge of nitrate is? 1. And lead, the 2 up here tells you the lead has what charge? 2. So pbi2 plus with NO3 -1 gives you a compound of Pb
NO3 2.
NO3 quantity 2. Okay. And this is a double replacement reaction. So remember, in a replacement reaction, double replacement. In a single replacement, one thing kicks out something. In a double replacement, they switch partners. So A plus AB plus CD becomes AD plus CB. So you're going to make the precipitate PB. What's the formula for lead iodide or lead-2 iodide?
pbi2.
pbi2. Because again, iodine is a -1 charge. This is going to be our solid. And then the stuff that's going to stay when we do our second filter, that's going to go through the filter is KNO3. Okay. And this is going to stay aqueous. Is this balanced?
No.
Not quite. So go ahead and balance it. Doesn't take much. Blue goes with purple. Vegan. It's vegan and kosher. It's kosher sand and vegan wood. How did you balance this?
2 Ki and 2 KNO3.
2 Ki, 2 KNO3. All right. So now I gotta unpack what we just did. Okay. What you just wrote up here is chemistry 1 level stuff. You got a chemical and a chemical. You do a balanced chemical reaction, flip them with a double replacement, and you're done. You balanced it. Okay. Now here's what you need to remember. All halogens, iodine, chlorine, fluorine, bromine, have a -1 charge because they're in group 17. Okay. All alkali metals, sodium, potassium, lithium, rubidium, have a +1 charge. So far so good? Okay. The nitrate comes from oxygen having a -2 charge and nitrogen having a +5 charge. Wait a minute, nitrogen should be -3 because it's 3 over from the noble gases. Oxygen has a -2 charge and it forces nitrogen to have a +5 charge because oxygen is more electronegative. Okay? If 2 things that want to be negative are bound together, the thing that is more electronegative gets to be negative. And remember, fluorine is our most electronegative, followed by oxygen and chlorine, and nitrogen, sulfur, and bromine. Okay? But the big one is oxygen. When oxygen is bound to something that's not fluorine, it gets to be -2, forcing the other thing to be positive. Now, if oxygen was bound to fluorine, fluorine would get to be -1, forcing the oxygen to be +6. Pretty rare, but it does happen. Okay. So since oxygen is more electronegative than nitrogen, oxygen gets to stay -2, forcing nitrogen to be +5. That's why nitrate is -1. Can you see that in your mind's eye? Okay. Again, we're going to give this a deeper treatment. Right now, we're just kind of adding bits and pieces. Now, here's the thing, solubility. The reason that lead iodide becomes a precipitate is that lead compounds are almost always insoluble. They want to fall out of solution. But more important than lead, nitrate and potassium are always soluble. Nitrate compounds are always soluble. Anything bound to a nitrate is going to be soluble, will dissolve in water, which is why lead nitrate will dissolve, but lead iodide will not. Does that make sense? Last year, you played with silver nitrate, and we're going to use it this year too. Silver nitrate will dissolve, but silver anything else will not. Silver does not want to dissolve. Gold nitrate will dissolve, gold anything else will not. So nitrate is the king of being able to dissolve things. So lead nitrate will dissolve in water, lead almost everything else will not. Okay? The thing that will almost always, actually will always dissolve something is a group 1 or an alkali metal. Alkali metals will always dissolve in water. Okay? If it was potassium sulfide, that will dissolve in water. Most sulfur compounds do not dissolve in water. Does that make sense? And we're going to do a deeper treatment of this later on, but just at this early phase, just plant it away that nitrates make things dissolve and alkali metals make things dissolve. Okay, if this makes sense to you, give me a thumbs up. Okay, this is a pretty rich learning experience we were doing in the last 15 minutes. Thank you for remembering to record it. Next, there's this thing called a net ionic equation. The net ionic equation is the ions that make a precipitate. The net ionic equation are the ions that make a precipitate. Let me explain what's really going on here. This Ki is not a solid, it's aqueous. This lead nitrate is not a solid, it's aqueous. And when you say something is aqueous, what you're saying is you are not seeing Ki. What are you seeing? What's really in the beaker?
Solution.
Water and not Ki as a compound. Remember, Ki is not a compound. It's an ionic solid. It's made of ions. So if I took some Ki and I dumped it into a beaker and it was solid, I would have a bunch of solid ionic salt. But the moment I added water, I don't have that solid anymore. I have potassium ions and iodine ions. So when I see something that is aqueous, Ki, aqueous, what I'm really seeing is potassium ions and iodine ions. I'm not really seeing Ki. There's Ki aqueous is kind of like one of those really kind of fudgy things. If you say something is aqueous, what you're really saying is there's potassium ions and iodine ions. You're saying cations and anions. Okay, does that concept make sense? If you see a solid after it, it means those two ions have stuck together. Okay, this is sodium chloride solid. This is sodium chloride aqueous, dissolved in water. So if you see an aqueous, what you're really seeing are the ions. That's going to be a big deal. It's a huge concept that we're going to hopefully internalize to the point where we can't get it wrong. You know what they say? Amateurs do it till they get it right. Pros do it till they can't do it wrong. That's where we want to be. We want to get to the point where in come May, everything is just automatic. Like boom, 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 no problem. I'm not going to be rushed. I'm good. Okay, so if this concept makes sense, that if you see aqueous, you're really seeing ions, give me a thumbs up. All right, so if we were to write all this stuff out as ions, you would not show the balanced chemical equation. It would be a little bit different. It would be potassium ion plus iodine ion plus lead 2 plus ion plus 2NO3 oops, these are two of those, ions, goes to pbi2 solid. Because these ions are stuck together, plus 2 potassium ions, plus NO3, actually 2 NO3 ions.
Hello. I just sent him a text, but disregard it because I forgot we were discussing. I'm like, a lot of people, he's definitely a lot of people. Tomorrow for our PLC, do you mind if we use your room?
We always do.
I know, I figured, but Ms. Wagner wanted me to officially ask, but it'll be all the people that I supervise, so it's like
Oh, everybody.
12 total.
Yes,
Okay,
that's
cool. Okay, cool,
Sure.
thank you.
Okay, so can you see why this should be written this way? Ion, 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 ion. Ions that are stuck together. Perfect. Alexa, stop. Ions are stuck together. Ions, ions. This is called an ionic equation. Meaning, it's what actually goes on in the beaker. These mixture of ions come together, they form an insoluble salt, lead iodide. Again, still ions, but stuck together because they're insoluble. In other words, we'll talk about why they're insoluble in a bit, but just realize lead bound to almost anything is going to be insoluble, and then some ions left over. Okay. This is not the net ionic equation. Do you understand what net means with when you add or subtract, there's a net?
It's like the leftover, right?
Exactly, leftovers are results, precisely. It's total, leftovers, the results. So if you go into the shopping mall with $100 in cash, and you do a bunch of transactions, and you go out of the shopping mall with $20 in cash, you had a net change of -80. Okay. All the changes that happen. So you look at this and say, well, the net ionic equation is only the ions that made up the precipitate. That, and that. So the net ionic equation becomes 2I- plus, actually, let's do this properly. Let's put the cation first. Becomes Pb 2 plus 2I- makes Pbi2, don't forget the solid at the end. This is the net ionic equation. It is the equation that produces the precipitate and nothing else. All the other ions are called spectator ions, meaning they're there to get the chemical into the liquid. They don't participate in the reaction we care about. So the things that are not in the net ionic equation are called spectator ions. Oh, jeez. How many times did I don't do it on your lap? Some big messes. And the custodians won't clean the counters. They're like, it's too gross. We only clean dust. So, but I gotta do the lab. It's a great lab. Pop rockets. Great fun. Big ones. Okay. How are we doing? How are we feeling about this?
So that end equation is just, what was that, like the definition you gave it?
The net ionic equation.
Which is the leftover.
Yes. So this is an ionic equation. This is the net ionic equation, which is what makes up the precipitate. Because the PBI2 is what we're going to care about, what we're going to measure. And the ions that make that PBI2 are the net ionic equation. Okay? How are we doing? All right. What I'd like you to do is 3 and 4 on your own, and we'll do that tomorrow. So 3 is just stoichiometry, and 4 is really important. We'll talk about it, but go ahead and do a little research and figure out why silicon dioxide is insoluble. Why is silicon dioxide insoluble? It's one of the most insoluble things on the planet. You might remember that sand is under the ocean. It just sits there, doesn't dissolve. Glass, you can dig down thousands of meters and you're going to find glass from old ships, still there, doesn't dissolve. So why is silicon dioxide so hard to dissolve? All right, questions? All right, so polish off 3 and 4, read what you're doing, and then we're going to do this lab tomorrow. I wrote it. It's brand new. I'm very excited. I'm very excited to do it. I like to write labs that are better than the EP labs.